Hello everyone. Today we are going to learn about an important class of organic compounds which are called alcohols. Alcohols are represented by the general formula ROH, where R is the alkyl group. Okay? So, it is the hydrocarbon part of the molecule and this is the hydroxyl functionality which imparts special properties to these hydrocarbons. Okay. So, this is the hydroxyl group and we can say it is a unique composite of a hydrocarbon and a water molecule. So, these compounds have several important roles in our day to day life. They are a part of many important compounds and things which we use, such as varnishes. They are present in perfumes. They are also present in the hand sanitizers which we use these days, quite popular, and the alcoholic beverages. So, they are a part of several important compounds which we have been using. However, probably we need to learn something about their chemical structure and properties, and that is what we are going to do exactly in today's lecture. So, when we refer to an alcohol in general, the most common alcohol is an ethanol, right. So, ethanol is given by the structural formula CH3CH2OH. This is a 2 carbon aliphatic alcohol and in general it is prepared by the metabolic process of yeast. It is prepared by the fermentation of sugars. So, the fermentation of sugars yields ethanol and this is in fact one of the industrial ways of making and producing ethanol. So, you start with the sugar and in the presence of yeast, this is a metabolic process of yeast, we get ethanol as the major component along with the production of carbon dioxide gas. So, these alcohols are important as we are saying, and ethanol particularly is important because it is used these days as a fuel in cars. So, it can be a replacement of gasoline. In fact, ethanol gasoline mixtures can be used in varying amounts as a fuel in automobile industry. So, with this background of the importance of alcohols and their applications in everyday life, let us look at from the chemical perspective why they are so important class of compounds. So, alcohols, if I would say, they can undergo various functional group transformations and they are the raw material to a variety of different organic compounds which we can obtain starting from the alcohols as the basic structural unit. So, they are the raw material for several interesting class of compounds. So, starting from alcohol, we can do an elimination reaction. So, via an elimination reaction, the alcohols can furnish us what we know as alkenes. So, elimination reaction on alcohols can yield us different types of alkenes. If they can also act as a substrate for a nucleophilic substitution reaction. So, if we carry out a nucleophilic substitution reaction on alcohols, what we get can be a variety of substituted alkyl derivatives like alkyl halides or other compounds. Likewise, they can also undergo oxidation of alcohols by virtue of the presence of the hydroxyl group. They can generate variety of aldehydes, we can have ketones, they can also produce acids as well as the acid derivatives like esters. So, all these are the possibilities when we are starting with alcohols as substrates. We can even use them as a nucleophile. So, when they are used as a nucleophile in a nucleophilic substitution reaction, they even yield what we call as ethers. So, we can get ethers also from alcohol. So, these are the different functional group transformations which are possible on alcohols, and that is why we say they are such important class of organic molecules. So, what are some of the physical properties? Let us look at the physical properties of alcohols which make them so important compounds compared to the counterpart hydrocarbons. All right. So, the physical property is by virtue of the hydroxyl group. Okay. So, it is by the virtue of hydroxyl group that there are many differences you would find in a hydrocarbon compared to any alcohol. So, if you look at the structure of an alcohol, they have this unique ability to form what we call as the hydrogen bonds. So, this lone pair of electrons on oxygen which is electronegative, it and the hydrogen which is rendered electropositive, they have this unique ability to form hydrogen bonding between two molecules or more of alcohols, and because of this ability to form hydrogen bonding which could be intermolecular or intramolecular depending upon the situation of the hydroxyl group. So, it forms essentially intermolecular hydrogen bonding between different molecules of alcohols, and that is why they tend to exist as associated liquids. So, alcohols usually exist in form of associated liquids. In fact, they can also be used as protic solvents in many organic reactions. So, some of the implications of this hydrogen bonding is it is manifested in two of the important properties, the boiling point of alcohols and the solubility properties of alcohol. So, the solubility and the boiling point shows distinction compared to the corresponding hydrocarbon because of the possible hydrogen bonding in these molecules. So, let us look at the boiling point scenario. What happens to the boiling point of alcohols? If we compare the boiling point of an alcohol to that of a hydrocarbon or a corresponding ether for that matter, we say that the boiling point of the alcohols is much higher. It is much higher than the corresponding hydrocarbons or ethers of the same molecular weight. So, we can conveniently say that if we compare the boiling point of alcohols with that of a hydrocarbon or an ether of the same molecular weight, it is higher than them, and this can be easily understood in terms of the additional hydrogen bonding interactions. If we compare ethanol to ethane, then ethanol, as we all know, sorry, this is ethane. So, ethanol is a liquid at room temperature, and the boiling point of ethanol is plus 78 degree Celsius. Compare this to ethane, which is a gas at room temperature with a boiling point of 89 degree Celsius. So, this clearly shows such an increase in the boiling point because of the additional hydrogen bonding interactions. Also, we see that alcohols which are 12 carbon or more, they exist as solids at room temperature. So, not only can they exist as a liquid, the additional interactions make them exist as solids at room temperature. The other properties in terms of the boiling point of alcohols is similar to as we see in hydrocarbons, that as the carbon chain length increases, the boiling point of alcohols tends to increase. So, this is quite obvious because this is supported by the van der Waals interactions which the longer alkyl chains are going to have, thereby raising the boiling points. Also, as the branching in the carbon chain increases, as the branching in the carbon chain increases, again as anticipated, the boiling point decreases because of the reduced van der Waals interaction. So, these are characteristics similar to any other hydrocarbon, except for the fact that the hydrogen bonding makes the boiling point higher than the corresponding hydrocarbons or the ethers of same molecular weight for that matter. Let us look at the solubility properties of these molecules. So, by virtue of the hydroxyl groups, these compounds are polar in nature. They are polar in nature, and as we know that if there is a polar compound, it will be soluble in a polar solvent. So, in the original form, if these alcohols exist as hydrogen bonded associated liquids, and if we compare it to the structure of water, which also has an intermolecular hydrogen bonding in which it exists. So, both are polar molecules, and if alcohol has to dissolve in water, then it has to form new hydrogen bonds with water molecule. For this dissolution to take place. So, overall it means that for this solvation or the ethanol or any alcohol to be miscible in water, the delta H solvation should be greater than the delta H required for dissociation of the alcohols, the dissociation energy required for breaking these hydrogen bonds and the dissociation energy required here for breaking the hydrogen bonding in the water molecules. So, if this exceeds, then the substrate alcohol will be soluble in the solvent. And also we witness that the alcohols with longer alkyl chain. So, we are talking about, so it has two parts, the hydrophobic alkyl part as well as the hydrophilic hydroxy group. So, alcohols which have a longer alkyl chain are dominating in the hydrophobic part and they are immiscible with water. So, this miscibility and solubility in water is only by virtue of the hydrogen bonding interaction between the polar group and the OH of water. All right. So, if you have understood these physical properties, let us move on to classify the alcohols. Let us understand how can we classify the alcohols based upon the number of hydroxyl groups present in them. So, the classification which we are going to discuss now is based on the number of hydroxyl groups present in the alcohol. So, based upon that we can have an alcohol with one hydroxyl group which we call as the monohydric alcohol. So, it is an alcohol with one hydroxyl group given by a general formula CnH2n plus 1 OH. It could be an alcohol with two hydroxyl groups which we say is a dihydric alcohol and given by the general formula CnH2n 2 hydroxyls, or it could be a trihydric alcohol with 3 hydroxyl groups, or it could be more than 3. So, we can always have a polyhydric alcohol. So, if multiple hydroxy groups are present, can be a polyhydric alcohol. So, based upon that, their properties, the physical properties, their solubilities, the boiling points change as well. So, we say that as the number of hydroxyl groups in the alkyl chain increase, okay, from 1 to 2 to 3, 1 the properties, the boiling point, what is the implication? The boiling point increases and the miscibility with water as expected also increases because of many more hydrogen bonds. It can, the multiple hydroxy groups can form. So, the miscibility with water increases as well. So, a typical example would be that of ethylene glycol, which is a dihydric alcohol. It is a 2 carbon dihydric alcohol. It boils at 197 degrees centigrade. So, if we compare it to ethanol, there is a substantial increase in the boiling point of this molecule by virtue of an additional hydroxyl group. Okay, so, in the monohydric alcohols, we have a further sub classification. So, all those hydrocarbons bearing one hydroxy, they can further be classified as a 1 degree or a primary alcohol, which means that the hydroxy group is attached to a carbon which is monosubstituted. So, we have a monosubstituted carbon to which the hydroxyl is attached, it is called a primary alcohol. We can have a secondary or a 2-degree alcohol in which the hydroxyl group is attached to a carbon which is disubstituted. So, there is one hydrogen and there are 2 alkyl substituents, or it could be a 3-degree or a tertiary alcohol where the hydroxyl is attached to a carbon which is trisubstituted. So, based upon that we have different classifications of alcohols which we will be using subsequently in the later part. Okay, so let us look at the structure of these molecules. What is the structure of alcohols in general? So, alcohols shown by the molecular formula ROH. The carbon is sp3 hybridized carbon, the oxygen is again sp3 hybridized. So, if you just look at the oxygen electronic configuration, O8 is 1s2, 2s2, 2px, 2py, 2pz. So, with the sp3 hybridization on oxygen, we get a tetrahedral arrangement in which there are 2 lone pair of electrons on the oxygen and there is 1 electron each in one of these hybridized orbitals, which then bonds to the R, the carbon and the hydrogen to give this alcohol, and the theoretically the angle, the bond angle ROH theoretical is expected by virtue of the tetrahedral structure to be 109.5, but experimentally this angle has been found out to be close to 105.5 degrees. So, this decrease in the bond angle from the theoretical to the experimental values can be seen in terms of the lone pairs, the 2 lone pairs which are available on oxygen, and by virtue of this lone pair repulsion, this bond angle, the ROH bond angle squeezes and we see a lower experimental angle. All right. So, going ahead to some important part, the property of these molecules is the acidity and the basicity behavior of alcohols. So, let us see the acidity and basicity behavior of these molecules. So, as we know that acidity is nothing but the ability of the molecule to lose a proton and basicity is its ability to accept a proton. So, let us look at the proton donor and acceptor abilities. The pKa values of the alcohols roughly fall in the range 16 to 19, which tells us that they are weaker acids than water. So, they are weaker acids than water, and if we compare their acidity with the known acid like a carboxylic acid, then you can see, and we all know that any aliphatic carboxylic acid aqueous solution, if you treat this with a base like sodium bicarbonate, which is a weak base. So, when we treat any carboxylic acid with a weak base like a sodium carbonate, we get the sodium salt of that acid, we get the corresponding carboxylate anion along with the formation of carbonic acid. So, we form this weak acid which dissociates to give us carbon dioxide and water. So, whenever we have to confirm the presence of an acid, we add sodium bicarbonate and we see the effervescence, we see for the presence of effervescence, which is an indicator that the compound, organic compound in question is a carboxylic acid. But if we run a similar experiment on an alcohol, I am afraid we do not see a similar result, which is quite explainable because alcohols are much weaker acids as compared to the carboxylic acid. So, if we have to test for alcohols, one of the tests is that you treat it with a reactive metal. You treat it with a reactive metal, the metal could be a sodium, potassium, magnesium, aluminium. So, any of these reactive metals, when you treat the alcohol, you get the corresponding metal alkoxide. So, we tend to get these metal alkoxides along with generation of and evolution of hydrogen gas. So, this shows that they do have acidic properties, but they are much less acidic compared to the regular carboxylic acid, and this property can be used for making all these metal oxides which are used as bases. Some of the most used ones are, we probably have come across different places, is like something like a sodium ethoxide, which is used as a base in many organic synthetic reactions. Aluminium isopropoxide, so this is trivalent aluminium, and we also have very popular, which is potassium tertiary butoxide. So, all these are used as bases in different reactions. Something about the basicity of these molecules. So, this is the acidity. They are much weaker acids than water, we have claimed, and if we have to compare the relative order of acidity of the alcohols with amines and water, so we would we could rate it that in terms of the relative order of acidity, water being the strongest, followed by alcohol, followed by ammonia, followed by a hydrocarbon. So, this could be the relative order in which the acidity could be rated, and the basicity of these molecules, the ability to abstract a proton, to get protonated, is because of the presence of the lone pair of electrons on oxygen, which can take up the proton, get protonated and form this kind of a cationic intermediate, which you will come across in many chemical reactions. The acid catalyzed reactions of alcohols, all of them go through formation of this kind of intermediates. And if you have to compare the relative basicity of the counter anions of the acids which we just discussed, so between the hydroxide, the alkoxide, the amide and the carbanion, the order of the relative order of basicity, if we can predict, would follow the order, this being the strongest base and hydroxide being the weakest base. We will discuss this in more details with examples in subsequent sections. Okay. So, with this brief introduction to the physical aspects of alcohol, let us move on to some of the chemical properties dealing with their preparation. So, the preparation or the synthesis of alcohols is important. As I told you, they are important raw materials for so many reactions involved in our day to day life to get important molecules. The preparation essentially is from three important starting precursors. One is starting from alkenes. So, we will discuss the preparation of alcohol starting from alkenes. Through the reaction on alkenes is the electrophilic addition reaction. Electrophilic addition on alkenes gives alcohols, and this could either follow a Markovnikov's pathway or it could be an anti-Markovnikov addition. So, we have the Markovnikov and anti-Markovnikov addition and conversion of the alkenes to alcohols through electrophilic addition. Okay. The other important substrates are the alkyl halides. And alkyl halides can again be converted to the corresponding alcohols through substitution reactions. So, substitution of alkyl halides can yield us alcohols, and this again can go via SN1 or SN2 pathway. All right. And the third in the list is the carbonyl compounds, very important. They are the backbone of the organic synthesis. The carbonyl compounds, they can also yield alcohols, and now in this case it is through a nucleophilic addition reaction. So, the nucleophilic addition onto the carbonyl double bond C double bond O the nucleophilic addition on the carbonyl compound, either again through different reagents, could be lithium aluminium hydride, strong reducing agent, could be the milder one, sodium borohydride, or even the addition of the Grignard's reagents can give us a variety of different alcohols. So, this is the layout, the important starting materials for alcohols, and now we will take up each of them one by one. So, let us see, when we start from alkenes, what are the different options and possibilities we have for making alcohols. So, with alkenes as the starting substrates, the most convenient way. So, if you just look at it carefully, the alkene has to be converted to an alcohol. So, it is nothing but it is addition of a water molecule across the carbon-carbon double bond. So, there are different ways of doing this. A direct way would be, which is, as you can see, you directly add water molecule to it. So, what we say is we can do direct hydration of alkenes. Okay. So, hydration of alkenes is nothing but addition of water. So, you take the alkene, any alkene, let us say we are working with a 1-propene as an example, and you treat it with water, and this is usually an acid catalyzed hydration. So, you do an acid catalyzed hydration. So, the first step would be addition of, from the sulfuric acid unit, the proton and HSO4 onto the carbon-carbon double bond, and this is followed by replacement of this HSO4 by the OH unit from the water, and we get this corresponding alcohol, which you can now see for yourself is a secondary alcohol, because it is attached to a carbon which is a disubstituted. So, what we call here is that the overall effect is addition of water molecule, and hydrogen from this acid, it has gone to add on to the carbon which already had more hydrogens attached to it. So, that is why we call that this product is a Markovnikov's product. It is a Markovnikov's addition. The product is a Markovnikov's product, where in general all this hydroxy group always goes and adds on to the carbon, which forms a more stable carbocation. This is the general principle. So, we usually gets the Markovnikov addition as the dominant pathway for all these addition reactions on alkenes, giving us alcohols, for example, in this case. The other important process which is industrially relevant as well is the oxo process for making alcohols. All right. So, in the oxo process, we start with the alkene, treat it with carbon monoxide, hydrogen gas mixture in the presence of a cobalt catalyst, which is octacarbonyl dicobalt. There is an intermediate formation of an aldehyde, which is subjected to reduction with hydrogen gas and nickel as the catalyst, and this furnishes what we say is an alcohol, and the alcohol is a primary alcohol. So, this oxo process is in fact an industrial process of generating these alcohols, and the important thing about this process as you would see here is that it helps in stepping up of the series. So, if we are starting with a 2 carbon system, let us say we are starting with an ethene and we treat it with CONH2 in the presence of the cobalt catalyst, the dicobalt octacarbonyl, we get an aldehyde which is now a 3 carbon aldehyde. So, there is a stepping up of the series, and this is followed by reduction to give you the 3 carbon alcohol, that is the 1-propanol. So, we get a 1 degree alcohol through this, because an aldehyde reduction would yield up a primary alcohol. So, this is a very important industrial process for making these alcohols. Okay. So, let us move on to the third important pathway starting from olefins. It is what we call popularly as oxymercuration, demercuration. And as the name says, you can see that it involves somewhere mercury in this reaction. So, in this reaction we start again with the alkene. We are talking about all the methods from alkenes for generation of alcohols. You start with an alkene, treat it with a mercury salt, which is a mercuric acetate in this case, and this is in THF water. In between we get an intermediate which is a mercurinium salt, and this is in the second step it is subjected to reduction. So, in sodium borohydride alkaline medium when we get the corresponding alcohol. So, it is a two step process. The first step is what is the oxymercuration, and the second step, which is the reduction, is the demercuration, which is the removal of the mercury from the intermediate salt which is generated. So, the reaction has certain important features. One, this reaction gives you alcohols through an addition which follows Markovnikov's addition. So, it gives you Markovnikov's product. It does not involve any carbocation. So, there is no rearrangement which is observed if you are making alcohols through oxymercuration, demercuration. There is no rearrangement because there is no formation of carbocation. So, there is no carbocation intermediate, which is because the carbocation has this unique ability to always rearrange to a more stable carbocation whenever it gets an opportunity. But in this particular case, since there is no carbocation generated, we do not see any rearrangement in the product, and this addition, the oxymercuration step, it follows an anti-addition. It is an anti-addition protocol. So, let us look at the sequence, the manner it follows in. So, you start with an olefin, you treat it with the mercury salt, mercuric acetate in THF water. So, this step involves loss of an acetic acid unit, and what you get in the middle is an addition product in which there is a hydroxyl added and there is HgOAc, which is the acetoxymercury which is present on the other carbon, and this now has to be reduced with sodium borohydride as the reducing agent to give the final desired alcohol, which overall involves addition of a water molecule on the carbon-carbon double bond. So, this is the overall oxymercuration demercuration reaction in which there is addition of this water molecule, as we mentioned that from in order to get an alcohol from an alkene, the overall process involved is the addition of a water molecule. Okay, so, let us look at some of the examples and the products which we expect to arise from these molecules. So, if you start with this cyclic olefin, which is a 1-methyl cyclopentene, and you subject it to this oxymercuration demercuration reaction, there are two possibilities. We can either get the product in which there is a hydroxy substituted on this side, or we can get a product in which, so this is corresponding to a methyl. So, in which there is a hydrogen and the hydroxyl goes on to the other side. So, of the two products, which is the product which is formed through this reaction. If you look here, in this case the hydroxyl is adding to the carbon which is more substituted, or in other words the hydrogen is added to the carbon which is already having more hydrogens, which is less substituted. So, we say that this is the Markovnikov's product, and we know that this reaction favors a Markovnikov's addition. So, this will be the only product. So, this is in terms of the regiochemistry of this reaction, it follows and allows you to get a Markovnikov's addition product. Okay, so if you look at another olefin, which is, it's a tertiary butyl. Okay, so if you have to number this, this will become a 3,3 dimethyl, 1, 2, 3, 4 and 1 butene. So this is a 3,3 dimethyl 1 butene, and if you again subject it to hydroxymercuration and demercuration, what we get in the process is an alcohol which will be this one, with hydrogen goes and add to the terminal carbon, and you get this product which is a 3,3 dimethyl 2 butanol. So you can see that there was a possibility of a rearrangement in this case to give you a more stable carbocation at this center, but no, there is no rearrangement, there is no rearranged product, there is no carbocation. So you get this exclusively as the only product which is obtained. So this is interesting. Let us understand, since a lot of this specificity is observed in this reaction, what is the mechanism that this oxymercuration demercuration is going through. So let us peep into the mechanism and try to understand some of the aspects associated with the reaction. Okay, so we have an olefin to begin with. Okay, so we begin with an olefin, and there is a mercury salt available in the form of mercuric acetate. So the first step is believed to involve this attack of this pi electrons onto the mercury salt Hg, and with the elimination of the acetate anion. The first step we believe is the formation of this kind of an intermediate, which is a 3-member intermediate. You have the mercury, which is forming a cyclic 3-membered cyclic intermediate with the 2 carbons of the double bond, this positive charge sitting with the mercury. This is a cyclic mercurium ion which is generated as the reaction intermediate. So you can see that there is a bridge formed on this side. Okay, so the next step, which is the attack of water molecule onto this cyclic mercurium ion intermediate, now has to be from the side other to the side from where the bridge is formed. So one side is blocked by formation of this bridged intermediate. So the water molecule attacks from the other side, and this results in opening up of the bridge and formation of, so if I have to show this, the OH2, it adds from the side opposite to where the bridge was, and we get this as the open chain analog of the cyclic analog. So the next step now is the, if you see, this is a trans addition. So that is why this is an anti addition. This is very selective, it is quite stereospecific. This follows an anti addition pathway. Okay. So the opening up, we have the mercury and the water residing on opposite sides. Okay. And if we see that the water molecule, it attacks onto the carbon which is more substituted. Okay. So it's attacking onto the carbon which is more substituted. So again there are two reasons that this carbocation will be more stable, one, and that is why it is attacking here, and the second is that the mercury would go on to sterically less hindered carbon. So it being a bulky group there, it will go and sit on the less sterically hindered carbon of the 2 carbons of the alkene. All right. So the next step now would be to take up this proton, which is done with the help of the acetate anion, which acts as a base, and it deprotonates this intermediate to yield to yield this intermediate in which you have a hydroxy on the carbon which is more substituted and mercury is on the carbon which was less substituted, and now is the last and the final step where we have the sodium borohydride reduction. Okay. So, in this step is where it loses the stereospecificity. So, the borohydride acting as a reducing agent, it reduces this mercury, right, it breaks the CHG bond. So, there is a breaking of the carbon mercury bond and there is a creation, a new CH bond takes its place. So, we have eventually the last step hydride from the sodium borohydride which replaces the HgOAc and we get finally our alcohol which is Markovnikov's product. So, this is overall what is expected out of the oxymercuration demercuration mechanism. It is also sometimes called oxymercuration reduction because there is a reduction involved in the final step. A very interesting reaction, the fourth one of what we have discussed from alkenes, which complements this oxymercuration demercuration, is a very popular reaction called hydroboration oxidation. So, hydroboration oxidation. It was for this reaction that H.C. Brown got the Nobel Prize for discovering this unique reaction called hydroboration oxidation. So, when I say that it is complementary to oxymercuration demercuration, why? Because you start from alkenes and you get alcohols which are anti-Markovnikovs. So, we get anti-Markovnikov product. So, this is interesting because this complements your oxymercuration demercuration. Alkene, treat it with boron hydride in a solvent like THF or ether, and what we get is an alkyl borane. So, there is addition of the boron onto the carbon-carbon double bond of the alkene. So, there is addition of the boron and hydrogen, we get an alkyl borane, and then this is subsequently followed by, again it is a two-step process. It is subsequently followed by the oxidation with hydrogen peroxide as the oxidant under alkaline conditions to give us finally the desired product, the alcohol and the boric acid. So, it has two components, again the addition of the borohydride over to the alkene is called the hydroboration, and conversion of this alkyl borane into the alcohol is the step which we call as the oxidation, and overall it involves addition of a water molecule across a carbon-carbon double bond to give us an alcohol which is an anti-Markovnikov's products. That means, we tend to get alcohols which are less substituted. Okay. Looking at how this reaction works, let us see and figure out. So, we have an olefin treated with borane. So, a borane usually exists in the dimeric form as a diborane. These reactions are executed in dry ether or THF. So, the first step is the hydroboration, that is addition of the boron hydrogen across the carbon-carbon double bond, and in the process what we get is something like this which we call as an alkyl borane. So, there is addition of one of the olefins across this BH adds across one of these olefins, we get the ethyl borane, and this step repeats because still we have two of these boron hydrogen bonds available for addition over an olefin, and this again repeats twice. It adds on to another molecule of ethene, we get dialkyl borane which is a diethyl in this case, and still we have a BH bond. So, the first step is that these boranes are Lewis acidic, we have a empty p orbital, and this pi bond they push their electrons into the empty p orbital of boron, which is why the first step is initiated. So, this adds on now to the last another molecule of olefin, since we have still a boron hydrogen available there, right, and finally what we get is a triethyl borane. So, this is the hydroboration sequence which goes one after the other, and there is replacement of all the 3 boron hydrogen bonds by the boron alkyl bonds, and that is why it is called a hydroboration reaction. All right. So, the next step is, once we get the trialkyl borane, it undergoes oxidation with hydrogen peroxide under alkaline conditions to furnish 3 molecules of ethanol, since we started with ethene as the starting olefin and boric acid. So, this is eventually what happens in the during the oxidation. So, if we start with let us say I will take the same examples which I took for oxymercuration, demercuration. I start with the same olefin and we carry out a hydroboration and oxidation on this molecule. So, the product which we expect to see from this is complementary to what we got for the other case. So, in this case again you will see the hydroxy group. Okay, so, this is a methyl, this is a hydrogen. So, you can see that in this case the hydrogen goes and adds to the carbon which is more substituted, and we get the anti-Markovnikov's product. Another interesting feature here is that we get addition through a syn pathway, we get a syn addition product. So, if I have to write the stereo chemistry of this product, then the hydroxy as well as the hydrogen, they add from the same side. So, I have shown them by the bold, the wedges, and this by the dashed. So, this methyl and this hydrogen are away from us. So, this follows a syn addition pathway. And if we do the other substrate as well, which we took for the previous case, in this case again the product will be the other way to what we saw with the oxymercuration, demercuration, and we get in this case again a primary alcohol. So, in this case we are getting a primary alcohol. So, this is how this hydroboration oxidation complements the oxymercuration, demercuration, and so important a reaction for obtaining the alcohols which are less substituted at the carbon. So, what is the mechanism? It is quite interesting to understand what is going on during the reaction that we are getting so interesting products. So, we believe, let us start with any olefin, and this is let us say I start with this olefin in which this carbon is substituted with 2 methyl groups, and this carbon is non substituted. So, we have 2 hydrogens shown with the dashed and the wedge, and this is treated with diborane or the boron hydride. So, the first step is the transfer of this electron density from the pi bond onto the electron deficient boron, the empty p orbital, right. So, the first step would be the attack here, and what we see is the formation of a 4-membered cyclic transition state. So, we have a methyl, there is another methyl here. Okay. I will not write these methyls on because it is kind of understood. So, only for hydrogens we put the hydrogens. So, the first step is that this formation of this carbon boron bond here. We form this carbon boron bond, and this boron is delta positive and the carbon gets delta negative, and it pushes this electron density. So, this carbon becomes delta positive, and now to satisfy this boron hydrogen, the other boron hydrogen, it transfers this electron density from hydrogen and works as a hydride and forms an additional formal bond with this carbon. So, we get this kind of a 4-membered cyclic transition state. So, there is formation of this 4-membered cyclic transition state, and this can explain the syn addition. And eventually, please remember that it is this boron which would get replaced by the hydroxyl group. So, there is formation of this cyclic 4-membered transition state, there is a syn addition. Eventually, this gives you this product which is the monoalkyl borane. So, there is a new CH bond here and this hydroboration. So, you have two hydrogens and you have added a boron onto this carbon. So, this is the first step of hydroboration where one of the BH bonds has been added across a carbon-carbon double bond. So, this step now is repeated twice with two more molecules of the olefin. It is repeated and what we get here is a trialkyl borane. So, if we just have to represent, so you have this hydrogen added up here and this gives you the trialkyl borane. So, this unit is attached to boron and if I just write starting from the alkene which we have, the trialkyl boron will look something like this. So, you have boron, now it is tri substituted. So, you have one alkyl group here, then you have another alkyl group and you have a third alkyl group. So, if you just have to give the general representation, what we get here is a R3b where R is equivalent to this alkyl group, okay, and this is connected to boron. Okay, so, this is what happens during the hydroboration when you end up with the trialkyl borane. Now, the next step is the oxidation in the presence of alkaline hydrogen peroxide, when this trialkyl borane now reacts with hydrogen peroxide under alkaline conditions to yield the corresponding alcohol and there is this formation of hydroboric acid. So, what is happening here in the alkaline conditions? The first step is that your hydrogen peroxide with hydroxide anion to give you the hydroperoxide anion. So, this is actually the active nucleophile which is generated in the reaction which initiates the oxidation process. So, you have the trialkyl borane now with the boron having the empty p orbital and the hydroperoxide anion which is generated, all right. It transfers its lone pair of electrons into the empty p orbital of boron by acting as a nucleophile and this is what triggers the reaction and we get a boron which is a tetravalent boron with the hydroperoxide unit attached here. Boron bears a negative charge and you have the three alkyl groups. This intermediate which is formed is quite unstable. It is quite unstable and then this OO bond which is here, it is unstable and this is stabilized by the transfer of this alkyl group from boron to oxygen. So, this carbon attached to the boron, it migrates from boron to oxygen with the elimination of this anion as the hydroxide anion. So, this is what happens during the oxidation process. So, we get a boron with two of these alkyl groups and there is an OR. So, we get this alkoxy borane and this alkoxy borane now the last step is left that we have to get the alcohol out of it. So, again this reaction is initiated with the hydroxide anion which is available there and it again attacks boron and we get again a tetravalent boron, a boron with one hydroxy, one alkoxy and two alkyl groups and a negative charge. Okay, so, now this is the last step when this OR is lost as the alkoxide anion, okay, and it gives us back this BOH R and R and the same is repeated. So, we get the alkoxide anion, okay, with the two lone pair of electrons here on oxygen and another and then the water which is available, we are using a THF water. This acts as the proton source and the alkoxide anion here acting as picks up this proton and get the corresponding alcohol and the hydroxide anion. So, here this step, this boron which is formed, this can further in the same manner just the way we started with this, it can again react with the hydroperoxide twice more and give us 2 more units of the corresponding alcohol along with the hydroxide. The mechanism of a hydroboration oxidation, very useful reaction, follows syn addition, it follows anti-Markovnikov's pathway and gives us alcohols which are primary in nature, difficult to obtain from other methods. Alright, that is what we do for this time, and next time we start with the other starting materials, the alkyl halides and the aldehydes and ketones for producing alcohols. Alright, thank you.